In special relativity, force is defined as the time derivative of relativistic momentum. That means force equals m naught multiplied by velocity divided by the square root of 1 minus v squared over c squared. And we're going to take the time derivative of that entire expression. Here, m naught is the rest mass, and c is the speed of light. Both of them are constants. Our goal is to show that this expression is equal to m naught times acceleration a divided by 1 minus v squared over c squared, all raised to the power of 3/2. Before we begin differentiating the full expression, let's take a moment to understand how to differentiate a composite function using the chain rule. Take a simpler example. The square root of 1 minus v squared. That's the same as saying 1 minus ve squared raised to the 1/2 power. It's a composite function because there's an outer function and an inner function. The outer function is the square root, or 1/2 power, and the inner function is 1 minus v squared. To apply the chain rule, we first bring down the 1/2 as a coefficient, then subtract 1 from the exponent. That gives us negative 1/2. So far, we have 1/2 times 1 minus v squared, raised to the negative 1/2. Then we multiply by the derivative of the inside. That is, the derivative of 1 minus v squared. That gives negative 2v times the derivative of v with respect to time. And since the derivative of velocity is acceleration, we simply write that as negative 2va. Now multiply everything together. 1/2 times negative 2va equals negative va. So the final derivative is negative va divided by the square root of 1 minus v squared. Now let's return to the full relativistic expression for force. We're differentiating velocity divided by the square root of 1 minus v squared over c squared. Since this is a fraction, we apply the quotient rule. The quotient rule says, take the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator, and divide all of that by the denominator squared. In this case, the numerator is velocity, and its derivative with respect to time is acceleration, a. So the first term becomes a times the square root of 1 minus v squared over c squared. Next, we subtract velocity times the derivative of the denominator. Now let's differentiate the denominator, which is the square root of 1 minus v squared over c squared. To make this easier, rewrite the square root as a power. 1 minus v squared over c squared raised to the 1/2. Using the chain rule again, bring down the 1/2, then multiply by the derivative of the inner expression, which is 1 minus v squared over c squared. Differentiating, that gives negative 2va divided by c squared. So now we multiply by 1/2, and we're left with negative va over c squared. That's the derivative of the denominator. Since we're subtracting v times this result, we now have negative v times a over c squared divided by the square root of 1 minus v squared over c squared. Putting it all together, the numerator becomes a times the square root of 1 minus v squared over c squared plus v squared a over c squared, and everything is over the same square root. We factor out a in the numerator. That gives us a multiplied by 1 minus v squared over c squared plus v squared over c squared. The v squared terms cancel out, so the numerator becomes just a. Now look at the denominator. We had a square root in both parts, so when combining them under the quotient rule, the square root is raised to the third power. So the full expression becomes acceleration a, divided by 1 minus v squared over c squared, raised to the power of 3/2. Finally, we multiply by m0, and we get the final result. Force equals m0 times acceleration, divided by 1 minus v squared over c squared, raised to the 3/2. And that completes the derivation.